Hey there, awesome physics students. Let's revisit our roller coaster situation to think about what happens if we add a realistic treatment of the energy that's lost to thermal energy because of friction along the track here. So first of all, let's look at the energy diagram with the circles and the rectangles for this situation. So in that scenario, we have the cart has energy, right? The cart itself starts out with some gravitational potential energy, and it has kinetic energy at the top too, because it's going 1 meter per second here. So this is the energy diagram for that. This is kinetic energy. And while it slides or rolls down the hill here, some of the energy is converted into kinetic energy at the bottom, but there's also some energy that becomes thermal energy of the track here. So to draw that, we would say the cart has kinetic energy at the bottom, and then some of that energy is also converted into, well, the track plus the cart both gain some thermal energy because of friction. Okay, so then how do we actually compute this? Well, what we need to actually run this experiment and find the velocity at the bottom and see what that is and compare it. So if you recall, the velocity, the predicted velocity was 24.3 meters per second. And then let's say we actually run the experiment and we find it to be 22 meters per second. So we can use this actually as a guide. This will become an equation. So how does it become an equation? Let's draw it out here. So what we're saying is that the cart has gravitational potential energy, so that's mgh, plus it has kinetic energy, that's 1/2 mv initial squared, that's the initial velocity at the top. And then this conversion sign through rolling becomes an equal sign here. So that energy is converted into the cart energy, kinetic energy of the cart, so that's 1/2 mv final squared. This is the real velocity at the bottom, 22 meters per second, plus the thermal energy, and we don't have a nice equation for that. We're just going to call that thermal energy at the bottom. We want to find that thermal energy at the bottom. So how do we do that? Well, we need to move this to the other side. So let me subtract it from both sides, and that will give me mgh plus 1/2 mv initial squared minus 1/2 mv final squared is equal to that thermal energy that we want to compute. Okay, so we can actually put the numbers in here, and this time we actually really do need the mass. It doesn't cancel because it's not in the thermal energy there. So we need to, let me just put the numbers in without any units. So that's going to be 250 kilograms times 9.8 times the height is 30 meters plus half times the mass is 250 kilograms. The initial velocity is 1 squared, and then I subtract off the final kinetic energy, which is going to be 250 times 22 meters per second squared. And when I compute that final thermal energy, I will get I go ahead and punch these numbers into my calculator, and I'll get 13,125 joules of energy, or 13.1 kilojoules. Okay, so this gives me an actual estimate for the energy that's lost along the track, and I can actually look and see, use some computations to make a prediction about if I know the mass of the track and the properties of the track. I could estimate roughly by how much in degrees will the track heat up and think about whether that's going to be a problem for the participants in this roller coaster. All right.